Hi there everybody, Tim Price here. During lockdown I worked on a project for our garden. We've got a little garden in London where there's a shed in the corner, and in the shadow of the shed there's a little area of grass that never gets any direct sunlight, and I thought it would be a great project to create a project with a mirror on and reflect the sunlight onto that piece of grass during the day, and then see if the grass will grow. I worked on that project. It involved quite a bit of welding, lots of electronic design, stepper motors, and real-time clocks and calculation of the sun position, and that's what this video is all about, so please do enjoy it. So this gives an indication of the electrical schematic of the project. If we start in this left-hand corner, you can see it's fed from an AC main source which is fused. It goes through a transformer, 30 VA transformer, and then a bridge rectifier with a capacitor. This then gives about 12 volts at this point, and that is used along this route by the two stepper motor drivers, this one and this one. They take quite a high current, that's why you have to sort of get it out there. The low voltage, the 5 volts regulator feeds the chip and things like the Bluetooth module and the real-time clock. So if we start here, these are switches which when they're open are tied to 5 volts, and then when they're closed they're shorted to 0, and those are used for the limit switches for the vertical, and down here the horizontal motions of the mirror system. This is just the crystal that implements the oscillator for the chip so it works. And these are the stepper motor controllers. So the PiC chip has an enable, a direction, and it gives a pulse when it wants the stepper motors to step. That's all. The movement of the stepper motors is obviously all controlled in code, and each stepper motor driver has 4 lines out here which go to the stepper motors, which are shown here. So that's really the left hand side of the diagram. On the right hand side you've got the programming interface here, which everyone should be familiar with. You've got the Bluetooth module which needs 5 volts earth, the serial clock and the data in and the data out, the SDO. The PiC chip only it puts the COM receive on the same pin as the SDO. So what I've had to do is implement my own receive pin, which I've called R receive 2, and I've created my own pin for the clock as well. So I use these pins when I'm talking to the real-time clock, but I do use the transmit pin, which is available even when you're using the serial data for something else. So that really is how the whole chip and all the things which are connected to it all link in and work. This diagram shows the designs of the mechanics, the gearing that is implemented to make the stepper motors control everything. So to control the rotation, we use a stepper motor which is pointing vertically up. It then runs a gear, a large gear here, and that's on the same shaft as this small gear, which goes to another large gear which drives the final what I call the azimuth rotation shaft. That's the thing that rotates the whole head of the mirror system, i.e. the bit with the mirror on. It's got a notch here to lock it properly so it doesn't just rotate on the shaft, and I've also put a couple of pins in this final cogwheel, and those pins press on switches to the limit switches, which indicate where the range for the motor. The vertical one is sort of shown here. So here the stepper motor is sort of on its side, and it drives this little cog here. That drives the big cog, which in turn drives a little cog on the same shaft. The little cog hits this rack here and makes the mirror angle. A pivot on this hinge makes it go in and out. That's essentially how it works. Oh yeah, I forgot to mention the Zenith end stop switches are on a gadget connected to the shaft here, and as the rack moves in and out, these end points, they hit the switches and stop the movement of the mirror. Okay, so this is the process that the code follows, that's implemented in the PiC chip. So when the PiC chip is first powered on, mains is applied, then it initializes the UART so it can implement serial communication via Bluetooth to anyone that's connected to it, and it puts out a little welcome message. It then reads the reference data from the EEPROM, so that consists of all the destination locations where you want the mirror to illuminate. It includes all the reference data about the endpoints of the movements of the mirror vertically and horizontally and that sort of information. And it also includes the physical location of where I'm sat now, where the mirror system is. Right, once it's done, it's read the EEPROM, then it goes to the real-time clock and queries that to get the date time now. It feeds the date time into a calculation which calculates where the sun is. Now I must admit I didn't write that function, I downloaded it, so thank you to the person who wrote it. Anyway, it then asks the question, is the sun in the data in the window where I can see it? So it uses a combination of the sun's position and the reference data that it's retrieved from the EEPROM. I imagine it's early in the morning and the sun hasn't yet come up, so the answer to that question will be no, and the mirror system would turn left. It would then move mirror home, but when the mirror is not active, when it's asleep, it's in a resting position, which is the home position, so it probably won't do anything when it hits this move mirror home. It writes a log message to say where the sun is, where the mirror is, how much it moved in its last position change, and whether the mirror is asleep or awake. It then waits 30 seconds and goes around the loop again, reading the time, calculating the sun position, etc. So now imagine the sun has come round and it can answer yes to this question. It then comes and asks, have you already calibrated the system? That means, have you calibrated it today? It calibrates itself each 24 hours when it switches on. So the first time it comes down here, the answer will be no. So it runs this calibration routine, which I'll show you later in the video. Then it gets the destination from the EEPROM data and calculates where the mirror needs to be to reflect the sun's light onto the destination point on the lawn, and it runs this function here to move the mirror to that position. It then goes back and writes the log message, but this time instead of writing a 0 to say it's asleep, it will write a 1 to say it's awake, and it will delay 30 seconds and then carry on doing that loop for the daylight while there's daylight. When the sun disappears, behind a building or behind some trees or something, and the system reaches the end of it, and the sun reaches the angle at the end window, it will come down here and say no, the sun is no longer within the usable window, and it will then move the mirror home. So it goes to a sort of neutral position where it's can rest, and then it goes around here until it's time to wake up again the next day, and that's essentially what the main flow of the program does. It does have a few interactions you can use. You can quit the program, in which case it restarts again from scratch, and even if you do it in the middle of the day, it will run a new calibration routine. And that's done by pressing the letter Q in a Bluetooth connected COM session. If something's going wrong with the system, you can put a capital letter Q which halts it. I've never done that though. You can read the ref data from the EEPROM, which I will show you later the output that it produces, but essentially it reads the EEPROM and writes it out to the COM port. Also, you can update the date time. So this is used for initially setting the clock up. It shouldn't ever drift because it's a real-time clock, and it's got a battery backup, so you don't really use this function much. But what it does is when you press P, it says please enter a date time in this format and gives an example. What you should do is then paste a string into the COM window and press enter. The reason why you don't type it in is because the COM window is always writing the new log information, and it looks a bit messy if you're typing and then it writes a new data row. That's why I always paste and then click enter. It then validates the input, and if it passes validation, then it will update the clock to its new value, and that will be used when it next reads the real-time clock here. You can also update the latitude and longitude, which you don't ever do either really. You just set that once because the mirror system doesn't move to a different location, different house or anything like that. So when you put that in, it validates the input, and instead of and what it does, it writes it to the EEPROM for use. You can update the start and the stop angles. So these define the angles that are used in the sun calculation to say, is the sun in the window? It's that sort of thing that they're used for. You can update the switch value ranges to say, in the code which calculates the direction that the mirror's pointing, what are the end points used in that calculation. So there you say the horizontal left is a certain angle and the range is like 180 degrees, and the vertical is, its one range is minus 30, that's its bottom position, and it can go up to say plus 25 or 30, that sort of thing. You can also update the destination locations. In that case, what you do is you provide 12 pairs of locate coordinates. Each pair is used for a 5-minute window in the hour, and this allows for you to have the mirror system illuminate a different area of the garden each 5 minutes during an hour. And when it's done any of these interactions, it always returns to the main program. Switched on. So what it does, it calibrates itself doing the horizontal movement, so it's found one end there. then it goes the other way. So it does this once per day when it switches on, when it wakes up, and that's just to calibrate all the different movements. And now it's calibrating the vertical position, so it goes to the extreme. Oh, it's fallen over there, but it might come up. There we go. And now it moves to the first position for the day. So it goes round horizontally and then it should go round vertically. Normally it doesn't fall over like that because it's screwed to a wall. So there we are. Now it's ready to go and it will be reflecting the sun properly. So here you can see that it's been running for a while. It's alive, so it's putting one out at the end of every row. I've clicked R, which has caused it to output all this data. And so we just look at that. You've got the longitude and latitude of this location where the mirror is. You've got the window start angle. You've got the window start inclination. But what I've done is I've set that to 0. So I'm saying whenever the sun's above 0 degrees, then I want it to work. And the window end angle is set at 310 degrees. The H0 and H range define the start, what the start of the thing corresponds to, and its range. So it's saying at one extreme it's 142 degrees, and the H range, it has a range, it can go right the way halfway around the circle, 182 degrees. The 0 bearing, when it's at its lowest position, that will correspond to minus 24 degrees, and the range for the vertical position is 50 degrees, so it will go sort of from minus 24 to plus 26, that sort of thing. The target values, it shows the bearing and the inclination as a pair, and you can see there are 12 pairs here, and I set it up so it alternates between two different values. It goes 182, 197, 182, 197, and this goes 3420, 3420, like that. That makes the mirror do quite a big move each 5 minutes. The bottom two numbers, the 94 and the 227, are, I believe, the number of pulses per degree to make it move in the vertical plane and in the horizontal plane. You can see that the horizontal plane is a lot bigger than the vertical plane, so you've got a much finer movement on the horizontal plane because it's made up of several gears. It's got one more gear, I think, than the vertical plane. Okay, so what we're looking at here is a whole day run of the mirror system. This top left is the first one in the morning when the sun just comes around and just the corner of the mirror is catching and reflecting onto the garden. And then you go down here, a bit more of it, a bit more again, bit more, bit more, bit more, bit more, bit more, bit more. And then as you go across, you see the whole of the sun is reflecting on the mirror, you know, sort of here. I think here there's some hedges or something which you just catch in the bottom. The sun must have been quite low. Then as you go across, you see it's the whole reflection of the mirror as the day goes on, and then towards the evening when the sun probably goes behind some trees, you see less and less of the sun, and then it disappears in the evening. Right, so let's go back and have a look at it again. Oh God. So let's look at that tree here, this one, and look at the position of the mirror. So where is the mirror in relation to that tree in all of the pictures? Here it's wandered a bit to the right. Here it's back roughly where it was here. But what you'll see is it doesn't move too much. It moves a little bit with respect to that tree during the day, and it moves down a bit, but it's fairly stable. So that sort of tells me that the mirror system is basically working okay. So here you can see the tree, and you can see the reflection is still near the tree. Yeah, so that's it working for a whole day run. Now the clever ones amongst you will be saying, well, what happens when it rains? Surely the system will get wet and all the gears will start rusting and everything. Well, as you can see, I've made this metal thing, a dunce cap, which sits on top of the lighting system and keeps the rain off. Anyway, I hope you've enjoyed the video, and I'll see you next time. Goodbye.